Building software is a process of reducing abstraction. It means moving from a conceptual requirement into the physical reality of logic and code. When deadlines get tight, many developers try to skip the design phase entirely. They attempt to write functional code the moment they finish reading the requirements, hoping for maximum initial speed. This approach usually works for a few weeks, but as the codebase grows, functions begin to overlap, and variables lose their definitions, resulting in a tangled knot of spaghetti code. Eventually, adding a simple feature like a search bar can break the entire database. Fixing these bugs takes days instead of minutes, and the cost to modify the system climbs exponentially. Working without a design produces immediate technical debt. Managing that debt effectively depends on the specific methodology you use to organize your system. Most workflows fall into two camps. Top-down defines the master architecture first. It's highly stable, but creates extreme rigidity if requirements change. Bottom-up builds isolated components first. It's faster to start, but risks massive fragmentation if the parts don't connect. Relying on either extreme alone forces a trade-off between a rigid, slow-moving monolith and a pile of parts that don't fit together. To understand how these components work, we have to look at object-oriented design. This is the mechanical engine that powers the bottom-up approach. The foundation of this engine is encapsulation. It allows you to bundle specific data and the algorithms used to process it into distinct, self-contained units called classes. Encapsulation makes modules highly cohesive, but overusing it creates its own problems. If every class is too isolated, simply retrieving data across the system becomes a complex task of navigating through multiple hidden layers. This leads to polymorphism. You can create a single interface, like a shape, and have circles, squares, and triangles all execute one single draw command in their own unique way. This reduces redundant code, making it easier to extend the system. You avoid writing new logic for every shape. However, deep inheritance trees are fragile. A minor change to a top-level interface can inadvertently break every connected class below it. To avoid this, developers use the open-closed principle. This rule states that your code should be open for extension, but closed for modification. While this protects your core logic, it forces you to rely on heavy abstractions. This can make the codebase much harder for junior developers to navigate and troubleshoot. These object-oriented tools are powerful for building individual parts, but those parts still need a way to connect safely to the rest of the application. Design patterns act as the bridge. They provide standardized templates to link those isolated classes into a cohesive system. These patterns, whether they are creational, structural, or behavioral, give developers a proven way to solve recurring architectural problems without inventing a custom solution every time. Using a vetted pattern makes your code readable. A new developer joining the team can instantly recognize a bridge pattern and understand how the components are communicating. Standardizing behaviors through a pattern, like an observer or a singleton, creates predictability across the entire project. The danger is over-engineering, often called patternitis. This happens when a complex pattern is forced onto a simple problem that didn't need extra layers. Unnecessary patterns lead to abstraction bloat. You end up with a codebase that is needlessly rigid and difficult to follow. Patterns provide a great theoretical framework, but the practical implementation takes a significant amount of time and effort to get right. High-impact patterns only work if the entire team is already aligned on the broader architectural goals of the project. Patterns provide the logic for connecting your components, but they depend entirely on a clear architectural blueprint and solid classes to form a stable structure. Devoting your team to just one of these methodologies often leads to friction and a product that doesn't fit its requirements. If you only plan from the top down, you lose agility. If you only build from the bottom up, you lose global consistency. By combining methods, you get the stability of a master plan and the flexibility of modular components. This synthesis is meat in the middle. Top-down logic defines the grand architecture and subsystem boundaries. Then bottom-up design builds functional components safely within those predefined boundaries. This approach has become the industry standard because it ensures the architecture is sound while the individual features remain agile. To decide where your project lands, evaluate certainty against complexity. Some teams build enterprise systems or avionics software with rigid, legally bound requirements. These map to the high certainty quadrant. Because requirements won't move, these teams lean heavily into top-down planning, setting strict boundaries before coding begins. Other teams build web apps or startup products where requirements might change weekly based on user feedback. These projects land in the low certainty quadrant. They require a bottom-up approach with modular, polymorphic components, so features can change without collapsing the entire system. The most effective developers don't stay loyal to one methodology. They adjust their mix of top-down planning and bottom-up execution based entirely on the environment they're working in.